So now we're going to look at more specifically what are the physiological considerations for these different elements of the drug tracing that we're going to be looking at. So I have highlighted here in terms of blood pressure. Remember, we look at the diastolic blood pressure first, eliminate possibilities if we have a list of possibilities to pick from, then move on to the pulse pressure. Again, go through the same thing. Whatever possibilities are left, further eliminate, and hopefully you narrow it down to a very likely drug that you're considering, or you may have to take it further than that if you still are deciding. Now, for diastolic blood pressure, there are two physiological parameters that can affect the diastolic blood pressure. And so we can write those here, right? The diastolic blood pressure, okay, that's the minimum pressure in the aorta. There's a couple of things that impinge on this pressure. One would be the systemic vascular resistance. If the systemic vascular resistance goes up, the diastolic blood pressure goes up. If the systemic vascular resistance goes down, the diastolic blood pressure goes down. So this is a direct relationship. They go in the same direction. And the heart rate, which is also an important factor, that has a direct effect as well. In other words, if heart rate goes up, the diastolic blood pressure could go up. The heart rate goes down, the diastolic blood pressure can go down. Let's take a look about why this is the case using the Wiggers diagram that we still have up on the board here. Let's start with the systemic vascular resistance first. So you notice that after this dicrotic notch, and that's where the aortic valve closes, what's happening is the blood that was ejected from the left ventricle into the aorta is now running off to the various parts of the body. That's the systemic circulation. Now, as the blood is running off, the easier it is for the blood to go to those organs, the more rapid the drop in the pressure will be. Right? As the blood's leaving the aorta, right, the pressure's falling, as we can see here. So if we change the systemic vascular resistance, and remember the resistance vessels are primarily the arterioles, right? Those are the microcirculation, the vessels just before the capillary. If I change the radii or diameter of the arterioles through smooth muscle contraction or relaxation, that will influence the systemic vascular resistance and have an effect on the rate of decay of the pressure in the aorta. So what we can do here is illustrate two scenarios, right? Here would be an example of an increase in systemic vascular resistance. You can see that the decay in pressure is slowed, and I'm keeping the heart rate the same. Notice that the next cycle happens at the same spot, so I'm only changing one variable here. I'm changing the systemic vascular resistance, and you can see that the pressure ends up at a higher value, right? Remember, that minimum pressure is the diastolic blood pressure, so in this case, we've increased the diastolic blood pressure, and in this case, we've done it by increasing the systemic vascular resistance, okay? So this resulted in an increase in the diastolic blood pressure. All right. Now I could also look at the other side. What if I caused a drop in the systemic vascular resistance? Well, as I would expect here, this would result in a more dramatic drop in the pressure, and I would end up with a lower diastolic blood pressure. So this would be an example of a decrease in systemic vascular resistance. In this case, it would cause a decrease in the diastolic blood pressure. Again, I didn't change anything with heart rate or anything. I was just trying to look at one isolated change to show you why this is a direct effect, okay? And so to summarize, changes in systemic vascular resistance, which is achieved primarily by changing arteriolar tone, smooth muscle tone, that has an effect on this drop in aortic pressure during diastole. What about the heart rate? Well, you can actually get a pretty good idea about heart rate by looking at the next cycle and manipulating that. So you can imagine that in an example where this cardiac cycle happens sooner, so in that case the heart rate would be going up, so we can do that, right? So let's do a situation where now we have, this is happening earlier, right? Something like that. And do you see what I've done there? Do you see that it doesn't matter what's going on with the SVR? If I'm moving this cardiac cycle sooner, then I am making it so there's less time for the aortic pressure to fall. So in this case, this example here, where I've just drawn in this dotted blue line, this would be an example of an increased heart rate, okay? And because of that, it doesn't matter how the slope is going. If we want to look at the control value, right, the solid one, that's where we were before, do you see that I would end up with a higher diastolic pressure by virtue of the fact this is happening sooner, less time to drop. So in this case, this would cause an increase in the diastolic blood pressure in this example. And so again, that explains this relationship here. I want to point out that when we're looking at the tracings, all right, because we're looking at the heart rate last, in general, we don't really have to consider the effects of heart rate on diastolic blood pressure. It does complicate things more, and there is some variability in a lot of these tracings that we don't really address when we show an idealized one. So when you're looking at this for the first pass through, the way to look at this is to focus on the systemic vascular resistance change and not worry so much about potential effects of heart rate. This is a real effect. It certainly can have an effect on the diastolic pressure, but in most cases, we don't really have to consider it, and it actually may complicate how we are looking at these tracings. But it's good to show because it is a good, complete description of the things that can influence the diastolic blood pressure. Now, one other thing before we move on to the pulse pressure is, what are some receptors that we can think about in terms of affecting the systemic vascular resistance, in terms of receptors that we can stimulate, okay? So just for a review, what are some receptors that we can stimulate that can affect the systemic vascular resistance and increase it? Well, for example, right here, for example, this could be an alpha-1 agonist. Okay? So an alpha-1 agonist stimulates alpha-1 receptors. These are adrenergic receptors that are on vascular smooth muscle. They increase intracellular calcium, and that causes the vascular smooth muscle to constrict. And if we're talking about the arterioles, a vasoconstriction of those resistance vessels raises the systemic vascular resistance, and then that raises the diastolic blood pressure. So we would expect a drug that is stimulating alpha-1 receptors to cause an increase in the systemic vascular resistance and subsequently the diastolic blood pressure. What about examples that could cause a decrease in systemic vascular resistance? Well, staying with the adrenergic receptors, there are also beta-2 adrenergic receptors that are on vascular smooth muscle too. They're coupled to a different G protein signal transduction pathway, right? So the alpha-1s, they are coupled to GQ. That's why they increase calcium. The beta-2 receptors are coupled to GS. They cause an increase in cyclic AMP, and then that causes relaxation of the smooth muscle. And again, if it's in the arterioles, that vasodilation is going to cause a decrease in SVR, and we would expect a decrease in the diastolic blood pressure. So this would be something that would be something that's stimulating the beta-2 receptor. Another, and this is a example for that. Another receptor that we can think about is muscarinic 3 receptors. These are non-innervated receptors. So that means that there are no cholinergic neurons, no postganglionic neurons for the parasympathetic system that go to the blood vessels. There's no acetylcholine there to activate the muscarinic 3 receptors, but they are there. And the ones on the endothelial cells that cause nitric oxide release are very important, and you can activate those receptors through an injection of acetylcholine or a muscarinic agonist. And that nitric oxide release can cause an increase in cyclic GMP and vasodilation of those arterioles, and again, a decrease in SVR. So we can add a M3 agonist here as well. Okay. And then if you were going to try to think about antagonists, okay, you can certainly think of things that would impair the sympathetic system alpha-1 effects, like an alpha-1 antagonist, or something that was just impairing the sympathetic system, like a NN antagonist. Those sorts of things also we would expect the SVR to go down because you're just getting less alpha-1 mediated vasoconstriction. So this is not a complete list, but it's to get you thinking about when we're looking at a change, like in this example, which we will walk through. You see that the diastolic blood pressure is going up, and then that is going to help you, based on the drugs and what you know they do, to try to sort it out and eliminate possibilities. All right? So that would be our discussion for the diastolic blood pressure. Let's turn our attention to the pulse pressure. So the pulse pressure is the pressure that's added to the diastolic pressure. All right? So it's the pressure that's added. So actually, if we want to think about pulse pressure, we can think about pulse pressure. I'll do this right here. Pulse pressure is equal to the systolic blood pressure minus the diastolic blood pressure. And then if we rearrange this, right, we could also think of the systolic blood pressure is equal to the diastolic blood pressure plus the pulse pressure, right? It's basically just rearranging the math here. And one reason why you could do that is you can see that how high this pressure gets is going to be based off of two things. It's going to be based off of what the diastolic pressure was in the first place, but also how much pressure was added, all right? So that added pressure, that pulse pressure, is going to be influenced by things that make logical sense. When the aortic valve opens and the ventricle is ejecting blood, how much blood is ejected into that aorta is going to affect how much the pressure rises, right? So we call that amount of blood ejected by the ventricle the stroke volume. So certainly the stroke volume has an important influence on the pulse pressure. So we're going to go through the same exercise. We can just do this down over here, right? We have the pulse pressure, okay? This would be a positive relationship with the stroke volume, okay? Another thing that we can think about affecting the pulse pressure is not only how much blood is ejected into the aorta, but also how forcefully the ventricle contracts, because that increase in rate of pressure increase, remember the red aortic pressure here is following the ventricle pressure, and so if that ventricle pressure rises more rapidly and more dramatically, the aortic pressure is going to follow suit. And so that contractility of the ventricle is referred to as the inotropic state. So the inotropic state also has an important influence on the pulse pressure, a positive influence. Now, when you're considering these effects, the thing to keep in mind is that stroke volume is kind of complicated, right? Because there are multiple inputs onto the stroke volume that can cause it to go in different directions. So let me give you an example of what that means. So, for example, your afterload, that is how difficult it is for the ventricle to eject blood, and this is usually something that you could think of the pressure that the ventricle is working against as just a simple example. The more the afterload, the more difficult it is to eject blood, so that has a negative effect on stroke volume, okay? Heart rate. If the heart rate goes up, the amount of time to fill during diastole is mitigated, and there's less filling of the ventricle, and so that would have an effect to decrease stroke volume as well. So if you wanted to think about inputs onto stroke volume, okay, there are some negative inputs. This would be heart rate and afterload. And then on the positive side, preload, which is how stretched the ventricle is. So that's how much blood's coming back to the ventricle, and the more it stretches, right, the bigger the stroke volume. The less stretched, the less stroke volume. We call that the Frank-Starling law of the heart, Frank-Starling principle. And so preload, okay, and also inotropic state as well. Inotropic state, in addition to just the rate of increase in pressure, also has an effect to positively influence stroke volume. So we have also inotropic state, right here. This is a plus. So because stroke volume has various inputs, and then when we're dealing with some of our drugs, these drugs that we're going to be discussing can have opposing effects on stroke volume, where they're affecting, for example, afterload in one way and preload in another, and inotropic state in another. So when all those things are impinging on stroke volume, they tend to cancel out or mitigate each other. And so to kind of keep things simple, and this mostly works, you can mostly ignore effects on stroke volume, and you can just put your eye towards the inotropic effect. So when we're considering the pulse pressure, it's really, we can do this right here, it's really the inotropic state that we think about for the pulse pressure. And again, for the diastolic pressure, it's really the systemic vascular resistance is the key thing to focus on there. So like we did for the systemic vascular resistance, we could think about, well, what sorts of receptors are involved in regulating the inotropic state if we're just focusing on the autonomic nervous system, okay? Well, that would be the beta-1 adrenergic receptor. So this would be, for example, a beta-1 agonist. So remember, the beta-1 receptor on the ventricles increases cyclic AMP. It's a GS-coupled receptor, and that results in an increase in the contractility of the ventricle, and that would have a positive influence on the pulse pressure. So this is another important consideration when we're doing the analysis of the drugs. Knowing what receptors they act on and how they affect these different things are very important when we're going through step 1, step 2, and then step 3 and step 4. And remember, for these steps, you want to take a break, eliminate, go to the next step, take a break, eliminate. Don't just go all the way through and just try to pick one. It's always good to systematically try to rule things in and rule things out. And knowing now how these different physiological effects influence the diastolic pressure and the pulse pressure and which receptors are involved is going to be very valuable for us as we're going through and trying to assess from a list of drugs what could be causing the changes. And so what we're going to be doing next is we're going to be now considering how the mean arterial pressure and direct effects influence the heart rate. And what we'll have to do in that case is we'll clear off some space here and we will look at that in depth.